Hello friends, welcome for another deep learning project, Heart Disease Predictor. A model is developed using deep learning. It will take features of the heart of a patient and gives the result whether he or she has the heart disease or not. So moving forward, how I have developed this model and what are the steps I followed, that I am going to explain to you. At first, I have imported the libraries TensorFlow, Pandas, Keras. These are the libraries I have imported. Pandas for data manipulation, Keras for building the models, and TensorFlow is used internally by Keras. And from utils module of Keras, we have imported feature space. Feature space is for pre-processing the data. So as in scikit-learn we have column transformer, similarly in TensorFlow or Keras we have feature space for features transformation. Running this cell. Yes, it is done. Next, moving, I have imported warnings library to filter out the casual warnings shown in the notebook for different operation we perform. So filter warnings is a method in warnings library which is used to filter the warnings by providing ignore argument to it. After that, from Google I am downloading heart.csv and the CSV file link is here, and that is stored. File link is assigned to file URL variable, and using read CSV method of Pandas we are going to read the file URL and save it in the variable data frame. The next step is observing the data frame properties. In data frame properties we have shape, columns, preview, correlation, quantiles, unique values, and the data frame information. So let's go for shape of the data frame. So we have 303, that is 303 samples and 14 features. After that, using the columns attribute with data frame, we get the column names. So here we go, we have age, sex, CP, test BPS, cholesterol, that is call, FBS, rest ECG, thalak, exang, old peak, slope, CA, thal, and target variable. Let's see the first 5 samples of the data frame using the head method of Pandas and applied it to the data frame. So this is the first 5 samples of the data frame, and see we have 14 features in which target feature or target column is our output feature and rest are our input features. After that, we are going for correlation, and correlation is performed in between only numerical columns. So except thal column, all are numerical columns. So let's run this cell. So in correlation, we have to see that output feature is related how much with input feature. That is the main purpose of correlation. So here 19% related age to target, and sex is related 17% with target. CP is 38%, Trust BPS is 12%, cholesterol is 8%, ABS is 9%, rest TCG is 12%, and thalach is negative 38%. It means it is impacting negatively, oppositely. And exang 36%, old peak 47%, slope 35%, and CA 47%. So you should notice these things carefully. Moving forward, let's go for quantiles of the data frame. So here in first row, it is showing count of each column. So all the columns have 303 values in it. Then in second row, it is showing the mean of each column, each numerical column. And in third row, we have standard deviation of each numerical column. And in fourth row, we have minimum value in each numerical column. And then 25th percentile value, then 50th percentile value, then 75th percentile value, and at last we have maximum value in each column. So you should carefully observe column by column. I am moving forward. After that, going for unique values in each column. So these are the age unique values or ages of the patients. Then sex means the gender, and unique values of gender are 1 and 0, 1 for male, 0 for female. And then CP, in CP we have 1, 4, 3, 2, 0. These are the unique values, and to find out the unique values, we have to apply unique method of pandas to the column of data frame. And unique values of trust BPS are these values, integer values, and these are the unique values of cols, that is cholesterol, and 1 and 0 are the unique values of FBS, 1 for true, 0 for false. And next, unique values of rest TCG are 201. Similarly, unique values of thalach are these values, and unique values of exang are 0 and 1, 0 for no, 1 for yes, and these are the unique values of old peak, and it is in the range 0 to 6.2. The minimum value is 0 and the maximum value is 6.2. If you can observe it, you can find that. And unique values of slope are 3, 2, 1. Unique values of CA are 0, 1, 2, 3. Unique values of thal are fixed, normal, reversible, 1, 2, and unique values of target are 0 says that the patient is not diseased, and 1 for the patient is diseased. Moving, we are going for data frame info. So in data frame info we have range index, total of 303 samples, and index start from 0 to the 302. We have 14 columns in total, and one thing I want to say you that you should have to carefully observe the data type of each column, because when we create the user interface we have to match the data type of this with the inputs entered by the user. So always recheck what are the data types we have and what are the data types to which we should convert in user interface. So here we have one float 64 data type column, that is old peak, and we have 12 int 64 columns, and we have one object column, that is thal. Remaining are int 64. After that, going for data splitting. So we can use train test split, which is a function in model selection module of scikit-learn, but here I am going for another approach, that is simply selecting some samples randomly from the data frame using the sample method of numpy. Sample method will take out 20% of data from the data frame, as we have specified the argument frac equal to 0.2. Then we have random state equal to 11337. It means we have assigned a random state to the sample method. Assigning these 20% data values to a variable val data frame, that is val data frame is for validation data frame, and using the index of validation data frame data set, we are dropping these values from the data frame and storing the remaining data frame in a variable train underscore data frame. So val data frame is our validation data frame and train data frame is our training data frame. So let's execute it. After that, we can see the shape of these two type of data frames. So we have 242 samples and 14 features in train data frame. Similarly, we have 61 samples and 14 features in validation data frame. So to use feature space, we have to create dataset object from the data frame. So to create a dataset object from data frame, I am creating a function that is data frame to dataset and passing a data frame to it. Inside the function, I am copying the data frame to a variable data frame, and from that I am removing the target column using the pop method, and the target column is saved in levels. Then after using the from tensor slices, this is the method which takes a tuple, a list or any numpy arrays and creates a data set. So here I am providing a tuple. Inside the tuple I am giving two values. One is dictionary of data frame, another is levels. So after doing this, I am saving it to a variable ds for data set, and then I am shuffling the data frame with buffer size is length of data frame. If we apply train data frame, the buffer size becomes 242. If we apply well data frame, the buffer size becomes 61. So after that I am returning the data set. So applying, as I said, applying train data frame to it, we get train underscore ds, that is training data set, and applying well data frame, that is validation data frame, we get well data set. So let's execute it. Or to have preview of first value in the data set that we have created, I am running a loop. As we have generated a tuple, so I am taking out two variables x comma y. X is the dictionary and y is the level. So using take method applied to the data set, inside the loop I have a three print functions. The first print function is for showing input, then print another print to maintain a gap, and last print is for target, that is y. So let's execute it. So you can see we have, this is input a dictionary and target a tensor. So after that we have to batch the data set. So using the batch method and applying it to the data set, I am creating a batch of 32 elements and saving the same the original dataset variables. So train dataset and validation dataset are applied with batch method with 32 elements. Let's execute it. Batching is performed, and here is the most important step. We have to understand it carefully. So configuring a feature space. So as in column transformer, we specify the transformers, which transformer will be applied to which columns, that we specify in column transformer. Similarly in feature space, we have to configure, and so using the feature space method, inside it we have features an argument which takes a dictionary, and inside the dictionary keys are the names of columns and values are the pre-processing type which we use to that column. So we have categorical features, we have numerical features. So some categorical features are encoded to integers. So those categorical features are sex, CP, ABS, REST ECG, EXANG and CA. These are encoded as integers. Then we have string features, and this also a categorical feature. Thal feature is a categorical feature. We are encoding age string, and then age is a numerical feature. We are discretizing it, and some numerical features like trust BPS, call, thala, old, peak and slope, we are normalizing it. After that we have crosses argument. Crosses argument takes a list of tuples in which inside the tuple we have to provide the columns. Columns will be encoded combiningly, crossing each other, and that's why we have crosses. Sex and age are crossed each other, thal and CA are crossed each other. After that we have an argument crossing underscore di, that is for crossing dimension equal to, we have given 32. 32 means 32 new features are generated, or the dimension of crosses is 32. So using sex and age column we will get 32 new features. Similarly, thal and CA column also produce 32 new features. And finally, after pre-processing all, we are concatenating everything. Let's run this. The next step is to adapt feature space. As in column transform, we have to first fit it, then we have to transform using the fitted column transformer. Similarly, here we first have to adapt the feature space, then we can go for pre-processing. So without labels, I am adapting the training data set. I am adapting the feature space with the trained data set. So to remove labels, I am using a map method. Inside that I am applying lambda function and saving it to train ds with no labels variable and passing it to the adapt function of feature space. So let's run this. It is done. So we have adapted the feature space with the training data without any labels. So again we are using take method. Using that we are taking first sample of training data and using feature space we are pre-processing it and printing that. So let's run this. So this is the pre-processed sample. So here you need to observe that we have the shape 32,131. So we have 32 samples or rows and 131 columns of the first sample and d type equal to forward 32. After that I am pre-processing training dataset and validation dataset. So as training dataset contains two things, one is a dictionary, another is a label. So dictionary becomes our x and label becomes our y. I am creating a tuple using lambda function in which the first value is feature space of x, the second value is y, that is label. After that I am passing another argument, number of parallel calls equal to tf.data.autotune. If we use it, it will automatically adjust the parallelism level and can potentially improve the efficiency of data pre-processing, and it will reduce the complexity. That is, it eliminates the need for manual tuning of parallelism level, which can be challenging to get right for various hardware configurations and dataset. And prefetch involves fetching data from the dataset asynchronously in the background and storing it in a buffer. This allows the training process to proceed without waiting for the next data batch to be completely processed. So benefits are, it reduces training time and it gives improved hardware utilization. So that's why I have the argument number of parallel calls to tf.data.autotune and prefetch, doing the same thing to both training dataset and validation dataset. After that I am saving that in preprocessed _train_ds variable for train dataset and preprocessed _validation_ds for validation dataset. So let's execute it. So data pre-processing is over. Then after we are developing two models. So in feature space we have an attribute or a method get inputs, which gives us the raw inputs that we pass to the model, and again another attribute get encoded features, which will give us encoded features, and those two are saved in ticked inputs variable and encoded features variable respectively. After that I am creating a dense layer using 32 units of neurons and with ReLU activation function, passing encoded features to the dense layer and saving the layer in X variable. Then I am adding a dropout layer with 0.5% of dropout and passing the output of the dense layer to it and saving the output in again X variable. And finally I am creating another dense layer with one neuron, and here I am using sigmoid activation function because the model classifies either the heart is diseased or not. So I am giving the output in the dropout layer to this dense layer and saving the output in the prediction variable. After that, using the model method of keras, we are creating a model in which inputs are encoded features and outputs are prediction. This is the model to which we will train. That's why I have saved it in the variable training model. After that, compiling the model with optimizer as Adam, loss is binary cross entropy. Loss is binary cross entropy because this is a binary problem. And in matrix I am using accuracy, and you should always specify the matrix argument in list. After that, I am creating another inference model for our inference purpose and using dict inputs as its input and outputs as the predictions. So let's run it and create the model. Yes, successfully we have created two models. One is training model, another is inference model. And if you have any doubt and how it is created, what are the steps it is following, you can go for model summary. That's what I have done here. So this is the model summary, and whenever you build a model, if you have any doubt, you can go for model summary. And then again, summary of inference model. So this is the summary of inference model. So these are the pre-processing steps the model carries out, as we are providing raw inputs to it. And after that, fitting the training model with pre-processed trained dataset and having 20 epochs and providing pre-processed val dataset for validation data and setting variables equal to 2. So let's train the model. So first epoch, second epoch, yeah, it is very fast as we have very less number of samples. That's why the model trained very fastly. So we can see we have 81.97% of validation accuracy after the final epoch. That means our model will perform well. So let's go for model prediction. So we are using inference model to predict, as we want the users to enter the input values. So as users enters the input value, those values will be raw values and won't be pre-processed. That's why we are using inference model. If users enters the pre-processed value, then we won't use this inference model. The purpose of creating inference model is to use raw values. So I have created a dictionary with all columns and its values and saved it in a variable sample, creating an input dictionary using convert to tensor. So in sample items we have keys as columns and values as column values. So taking out all values and converting them to tensor using the convert to tensor method of TensorFlow and saving it in a dictionary, and its name is input dict. After that, providing that input dict to the predict method and applying it to the inference model and finding out the predictions, and at last printing the percentage of or probability of having a heart disease by the model. So let's run this. If a patient's age is 60 and is a male and have CP equal to 1, test BPS equal to 145, cholesterol equal to 233, FBS equal to 1, rest ECG equal to 2, thalas equal to 150, exang equal to 0, old peak equal to 2.3, slope equal to 3, CA equal to 0, thal is fixed, then he has 41.87% of getting a heart disease. And the final step is to save the model. Model saving. In Keras, we have a function save, which is used to save the model. So name of our model is inference model. So using save method, passing the file name to save the model. Hello friends, welcome back for the second part of heart disease predictor, and in second part we are developing an user interface so that users can use our model. So at first I am importing libraries like Streamlit, TensorFlow, Keras, Pandas and NumPy. Streamlit is to create the user interface, TensorFlow and Keras for model building, Pandas for data manipulation and NumPy for numerical calculations. After that I am loading the model using load model method of models module in Keras, and it takes the file path. So after giving the file path, I am assigning it to a variable called model. Then after I am creating the page, creating a container for heading. So using container of Streamlit, inside that I am creating two columns of different width sizes and assigning the vertical alignment to top and naming those two columns as image call and title call. Inside the image call I am providing an image of width 100 using the image method of Streamlit, and inside the title call I am creating a text using the write method of Streamlit and giving a title heart disease predictor in red color, and an emoji is applied to the heart. So to apply emoji you have to press Windows colons or Windows dot. After that I am creating another container for about the project section. So inside the container I am creating an expander where it is expanded by default and giving its label as what is this in blue color. So inside the expander I have written two write methods of Streamlit, and as usually the description of the project is written inside it. After that, I have created another container for entering the inputs of patient details. So inside the container I am creating another container without any borders, and after that I am creating an empty text area and saving it in the variable output. Then after I am creating 3 columns of same width size and naming them as age call, sex call, CP call, and these are the columns for inputs of the patient. So inside the age call I am having a age variable in which a text input will be given, and the text input is a method in Streamlit which takes a label argument. Here we have given blue colored bold age, then having a placeholder and its value is enter age here. As during model building we have seen that we have age of integer 64, that's why we are changing it to integer 64. After that we have sex call. Inside it we have a select box. Well, male and female are its options and gender is the label of the select box. Selected value is stored in sex variable. Then a if else block is created, inside which if male is selected the sex becomes 1, and if female is selected it becomes 0. Then a CP call in which we have a select box with blue colored bold CP label, and 0, 1, 2, 3, 4 are the options of the select box, and the selected value is stored in CP. Similarly, creating 3 more columns for trust BPS, cholesterol and FBS and naming them with adding suffix underscore call to each. Inside trust BPS call we have a text input, so the user should enter a value between 94 to 200 and it is converted to integer 64. Similarly, inside the cholesterol column the user should enter between 126 to 564. We can apply conditions, that is trust BPS should greater than or equal to 94 and trust BPS should less than or equal to 200. We can apply it, but I have not applied. If you want you can apply it. And similarly in cholesterol also we can apply same thing, but I have not applied. And in FBS column we have 2 options, true and false, and if it is true the FBS is equal to 1, and if it is false we have converted to 0. Similarly 3 more columns for STCG, thalars and adjunct values, and adding a suffix call to all columns. Inside rest ECG call we have a select box with options 0, 1, 2 and saving it in the variable rest ECG. Similarly for thalak we have a text input where an user can enter between 71 to 202 and saving it to thalak, and after entering we are converting it to int 64. Then we have adjunct column in which inside it we have a select box with options yes and no, and if yes is selected the adjunct will be 1, and if no is selected then adjunct will be 0. Then after we have 3 more columns, that is for old peak, slop and CA. So Inside old peak column we have a text input where user can enter values from 0.1 to 6.2. After that we have slope column where user can select options like 1, 2, 3 and saved it in the variable slope. Then we have a CA column where users can select 0, 1, 2 or 3 and saved it in the variable CA. Then we have created thal column. This is the final column, and another submit column. It's not required, but I have created to show the user interface more beautiful. Inside the thal column we have a select box where options are 1, 2, fixed, normal and reversible. Again I am creating a sample. It's a dictionary where column names are keys and its values are entered by the users, and if these values are entered, then a input dictionary is created. Using the predict method of model, we are predicting, and the input dictionary is passed to the predict method. The prediction of the model is saved in the prediction variable, and we are showing the heart disease percentage in the output, that is the empty space that we have created. So there we are showing a info status. After that I have created a container. Inside it I have created 5 columns with a small gap between each. So inside each column I have created a link button. In first I have created a link for YouTube. In second I have created a link for Hugging Face space, and third for a my personal page. Fourth is for repository of the project in GitHub, and fifth to connect with me in the LinkedIn. So these are the 5 columns or 5 link buttons that I have created, and in each link button I have provided 4 things. One is the label, another is the icon, the next one is the URL, and the fourth one is the help section. For now the Medi button is disabled and it will be enabled very soon. The project is done successfully. We have created it. To run this file and see the output, press Ctrl Tilt to open the terminal. In terminal we have to go for correct directory in which the file lies. So this is the directory. Let me check once again. So inside heart disease predictor we have app.py. So cd heart disease predictor. So to change the directory, press enter. Yes, directory is changed. Then to run the app, use Streamlit run and the file name and press enter. So the file is running behind and our app is generating. Let's wait for a while to come. Yeah, we got our user interface. Here you can see heart disease predictor is the title, and this is the image we have provided. And what is this? Heart disease predictor is a supervised DL model diagnosing heart diseases, and an artificial neural network is working behind the model. So we can close this expander. We have input sections like age to enter here. We have to select gender, we have to give CP value, we have to give trust BPS value, we have to give call value, we have to give FBS value, we have to give rest ECG value, we have to give thalarch value. Similarly, we have to give exam value, we have to give old peak value, we have to select slope value, we have to select CA value, and finally we have to select thal value. So entering age, let the age be 35. So let's select the gender female. So let the CP be 3. Let's her trust BPS be 150, and let's her cholesterol be 300. The FBS percentage of getting a heart disease is 93.98%. If thal is reversible, then the percentage is 98.92%. If thal is normal, then it is 39.41%. If it is fixed, then 98.88%. If it is 2, then 97.62%. If it is 1, then 93.98%. If slope is 2, then 81. Slope is 1, and 46. If it is 1, then 29. If it is 0, then 4%. If rest is equal to 2, 3%. If it is 0, 2%. If the gender is male, if CP equal to 4, 13%. If FBS equal to true, 26%. If exam equal to yes, 56%. If thal equal to reversible, 65%. If slope equal to 3, 92%. If CA equal to 3, 98%. If old peak equal to 6, 99.69%. So the project is over. Thank you very much for listening me patiently.